Okay, it's Module 7 time, and it's time to study electricity. And I want you to try something at home if you have the materials. And these aren't too elaborate. First thing you'll need is a battery. And it doesn't really matter what kind of battery. This is a D-cell. You'll also need a wire of some sort. Now this is a fancy wire that's got alligator clips to it, so it's kind of used in educational circumstances, but any wire really will do. And the last thing you'll need is a light bulb. And again, these tiny little light bulbs, little flashlight light bulbs, are quite appropriate for this activity. And the question is, using just these three items, one battery, one wire, and one light bulb, can you make the bulb light? That's your challenge. And I encourage you to, again, give it a shot, and I'll try to come back with a video that shows you how it's done a little later on in the module.
The second half of the course, starting here in Module 7, is slightly more abstract and perhaps a little more difficult for students because we start to deal with things that we can't actually see with our eyes. Up until now, we've been dealing with cannonballs being fired out of cannons, projectiles, cars crashing into things, blocks of wood that are floating in water. These things we can see, and when they're moving, we can start analyzing what forces are causing them to move. And if they're not moving, we can think about what are the forces that are still at play that wind up with a net force of 0. But it's very visual, the first half of the course. As we get into electricity, which is the topic of this module, of course, electricity is the result of moving electrons. And we can't see electrons. Electrons are too small to be visible to the human eye. So these are things that we're dealing with microscopic level objects. And so it can be a little more abstract, but don't lose sight of the fact that when things are moving, they're being forced to move. If electrons move, it's because they are being forced to move. They don't just move because they want to, they're being forced to move. And they're being forced to move because of what's called the electromagnetic force, which we'll be talking about. Okay, so here we have a couple of examples of charges. These are tiny little charges that are hanging from strings, and we have two examples, A and B. In A, we have two positive charges, and notice what's happening. Those two positive charges, they're like charges, and they are repelling. So that's one of the fundamental rules, is that like charges repel. And in B, you don't need Paul Abdul to tell you that opposites attract. The positive charge is being attracted to the negative charge. How do we know there's an attraction? How do we know there's a force going on here? What you should be doing is doing a little force diagram in your head. Again, don't lose sight of those force diagrams. If notice that my charge here on the left, my positive charge, let me change my color here. I think it'll stand out a little bit more. This charge over here that I'm outlining in red, it's at rest, correct? Again, why is it at rest? An object is at rest and will stay at rest if there is no outside unbalanced force on it. There are forces acting on this charge. It's got mass, and therefore it's going to have a certain amount of weight, right? The Earth is going to be pulling on it downward. What else is going on? We've got tension in the string. That's acting along the line of the string. So notice those couldn't balance each other out, because notice that the weight is a strictly downward force, and the tension force is kind of at an angle. Those couldn't completely balance out. And therefore, I must have one other force, and in this case, it is a force of repulsion acting to the left, which then balances everything out. So if I sum all these forces, I wind up with a net force of 0, which explains why my charge is not moving. Now, one thing that you should realize is that this force, this repulsive force, is a force at a distance. Up until now, we've talked mostly about contact forces, friction, tension, normal force, applied forces when you're pushing or pulling on something. But we also have a couple of forces at a distance. We've already dealt with gravity, right? The Earth can pull on stuff. It doesn't have to be in contact with the moon in order to exert a force on it. Likewise, this electromagnetic force, the force between charged particles, those particles do not have to be in contact with each other. This guy over on the right side that I just circled in green, he's the one who's influencing the one that I circled in red. They're not touching each other, and yet they can still apply forces to each other by virtue of what we call a force at a distance, the electromagnetic force. So at the heart of all matter are atoms, and atoms actually come from a Greek term for indivisible. So there's a famous Greek guy named Democritus, and he thought that if you chopped something up, chopped it 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 up, eventually you would get to a point where you could chop it up no more and have that same substance. So if you took a hunk of gold, you could chop it up, chop it up, chop it up, chop it up, chop it up. Eventually you would get down to an indivisible piece of gold, which he called the atom. And it turns out this is largely true, but we've discovered that there's actually stuff that is below atomic level. Atoms are actually made of fundamental building blocks. And those fundamental building blocks are called subatomic particles, including protons, electrons, neutrons. And that's what you see here. This is a very basic model of the atom, and it's just a model. It's not really the way things are, but it's useful for us to be able to visualize it because, like I said, this occurs at levels that we can't see. But all the stuff around us is made up of atoms. And in those atoms, you have protons and neutrons at the center of the atom, and you have electrons outside the center. Not necessarily in orbits. Sometimes they're displayed in orbits, kind of like planets going around the sun. That's not really the way it works, but it's a useful way of envisioning it. But one thing you should notice is that the the nucleus is positively charged because it's got protons in there. So the nucleus is positively charged. The electrons, the electron cloud, the electron shell, however you want to envision it, the electrons are negatively charged. So you might be wondering, asking yourself, why are the electrons not attracted to the nucleus? Why are the electrons able to stay out there? And that's because the electrons are zipping around. They've got very small mass. So just like the moon doesn't crash into the Earth, despite the fact that there's a gravitational attraction, the moon is also moving, and therefore it maintains a certain distance from the Earth. Likewise, these electrons are moving. They've got a certain amount of energy, and their motion keeps them from falling inward and crashing into the nucleus. Okay, so just so you get comfortable with the general structure of atoms, I encourage you to check out the first skill builder in this module, which allows you to build various elements. An atom of various elements, because each element has a specific number of protons in the nucleus. And you'll learn some other things about ions and isotopes and that sort of thing, but the main thing is you understand that each element has a specific number of protons. Typically, it has, for an uncharged atom, it has the same number of electrons. The number of neutrons can actually vary, and that will give you what are called isotopes. That's a little more than you need to know at this point, but play around with the skill builder and get a feel for some of the very basic elements that you're used to dealing with on a daily basis: oxygen, carbon, helium, hydrogen, etc., etc. Okay, so even though the motion of the electron keeps it from falling inward toward the nucleus, that's not to say there is no force there. There is a force of attraction, and therefore it would take work. You would have to actually pull on the electron to get it away from its parent atom. It turns out that different materials are more likely to give up an outer electron. Metals have outer electrons that are not strongly bound to the nucleus. They're relatively easy to remove. They're what are called free electrons. And if you recall from the heat module, I mentioned that metals are good conductors of heat energy because they have a lot of free electrons. Same story with electricity. Metals are good conductors of electricity. Think about the wiring in your home. What is it made of? Copper. Copper is a metal. Metals are good conductors of electricity because they have a lot of free electrons. So we have yet another conservation law in physics. We've already dealt with the conservation of momentum, the conservation of energy, and here we have the conservation of charge. And all this is saying is that charge can't be created or destroyed. It can be transferred. That's what's going on here. You rub a glass rod with a certain material, and you're going to rub electrons onto the glass rod. And if you've got a balloon handy, let's try out this demonstration.
Okay, so I wanted to talk a little bit about static electricity, and to do this demonstration I'm going to use a regular balloon. Nothing special about it. It's a nice purple balloon. And one thing that you should notice is that right now, if I put the balloon on my head, nothing happens. Right? The balloon just falls right off. There's no force. You know, if I, again, you should be thinking in terms of forces. So when I stick the ball on my head, all of a sudden it drops. Why? Because the balloon has weight and therefore it's being accelerated downward due to gravity. However, notice what happens when I rub the balloon on my head. When I rub the balloon on my head, something funny starts to happen. Now all of a sudden my hair, which was just plain old laying flat, is attracted to the balloon. Notice how my hair stands up. There's a force acting on my hair. And likewise, when I let the balloon go, notice that it sticks to my head. Why is that? It's not falling, right? The balloon still has weight. It should be falling downward, and yet it's not, which tells us that there must be another force at work here. And that force is the electromagnetic force that is described by Coulomb's law. We'll talk about that. Okay, here's another neat demonstration you can do using static electricity. Notice what I've got here. I've got a little stream of water. And that stream of water is, of course, falling downward. Why? Because water has weight and the earth pulls on it downward. But what happens, remember when I did this up with my head? And I charged the balloon, I scraped electrons off my hair, put them on the balloon. What do you think is going to happen if I bring my balloon close to that stream of water? Remember, that water's falling downward. Why? Because there's a force acting on it. But now all of a sudden, what happens? Can you see that? My balloon gets wet. But notice that the water bends. Right? Water doesn't bend just because it wants to. Water bends because it's being forced to.
This slide should take you down the amnesia lane, should take you all the way back to Module 4 when we talked about Newton's law of universal gravitation. Remember that gravitation is a force at a distance. Okay, so that means that two objects don't have to be touching to influence each other. And the way that they gravitationally influence each other depends upon their masses as well as the distance between them squared. Remember, it was a product of their masses divided by the distance between them squared, and there was a constant there, and the force was always attractive. Notice the similar setup for Coulomb's law, the force between any two charged objects. The electromagnetic force between two charged objects depends upon their charges. That's what the Q's stand for, as well as the distance between them squared. And then that K is just a constant. We don't really care about it. The one difference, so the general structure of the equation is the same. It's another force at a distance. The two objects do not have to be touching in order to influence each other. The one fundamental difference is that unlike gravitation, which is always attractive, electromagnetic force can be either repulsive or attractive depending upon the signs of your charges. Okay, so the unit of charge in the metric system is the Coulomb, and you're going to get a chance to play with Coulomb's law and find out the force between two charged objects and the distances and all that kind of stuff. You'll play around with this quite a bit in a skills test in this module called Coulomb's law. Okay, so you've already seen me stick a balloon to my head, and I'm going to got the same balloon, and what I'm going to do this time is I'm going to rub the balloon on my hair, again, getting electrons off my hair onto the balloon. So I'm going to turn this neutral balloon into a negatively charged balloon. Then I'm going to take it back to that wall back there, and I'm going to bring the balloon close to the wall. Now again, the wall is not a conductor. It's a neutral kind of material. It's essentially an insulator, really. But it does have charges in it. You know, it's got positive charges, negative charges. When I bring a negative balloon close to my neutral wall, the negatives in the wall, which are the more mobile, right? Electrons are much more mobile than protons are. They're much smaller, they're much less massive, and therefore they're going to be accelerated more by a force. So when I bring my negative balloon close to my neutral wall, the negatives are going to get pushed inward. They're going to be repelled by my negative balloon. That will leave the surface of the wall appearing to be positive. I'll have what's called charge polarization. The wall is going to appear to have a positive surface. Now all of a sudden I'll have a negative balloon close to a positive surface wall. and we're going to see a force of attraction which will keep the balloon hopefully in place. Now you should be doing a little force diagram. What happens to a balloon when I let it go? It should fall because of gravity. Let's see what happens. Well, nothing's ever perfect. Okay, this topic of electrical potential energy may seem kind of like inside baseball, but it is really important for you to understand a very fundamental electrical concept we call voltage. We're going to be running into voltage over and over again. You deal with it with batteries and 6-volt battery or 120 volts when you plug a lamp into an outlet. But in order to understand voltage, you have to understand the fact that charges can have potential energy. In fact, as you can see in the little diagram, imagine you have a block and it's sitting on the ground. In order to lift that block, you would have to do work, right? You would have to pull on the block to lift it because it essentially wants to be on the ground. In order to change its position in the Earth's gravitational field, you would have to do work against the Earth's gravitational field. You would give that block gravitational potential energy, and that's what's shown or labeled as PE here, right? Gravitational potential energy. Again, you would do work in lifting the block up, and you would give it gravitational potential energy. Again, it's just sitting there, it's not doing anything, but if you cut the string, notice that all of a sudden the gravitational potential energy turns into energy of motion. The block starts moving, right? And the only reason why it moved was because you had given it gravitational potential energy to begin with. The same thing can be imagined with charges. Notice that just like the block is attracted to the Earth, a positive charge here would be attracted to a negative charge here. They want to be together. In order to separate them, you would have to do work. You would have to pull on the positive charge to get it away from the negative charge. And just like a block, if you cut the string, is going to fall back to the Earth, likewise, this positive charge, if you cut the string, would start to move toward the negative charge because of that attraction. So we could say that charge, when we do have it lifted up and separated from the negative charge, has a potential energy. That potential energy is then turned into energy of motion when we cut the string. Knowing and visualizing that potential energy, the fact that charges, when separated, can have potential energy, is very important in understanding voltage. And this may seem like a semantic game here, but now that you understand what electrical potential energy is, now what you have to do is you have to divide the potential energy by the amount of charge, and you get a concept called electric potential. Because it turns out that in electricity, what we do is we essentially compare differences in electric potential in different parts of, let's say, a circuit. We're going to discover what circuits are in a few slides. But in a circuit, you have a difference in electric potential quite often. And it's very much like if you imagine a roller coaster. At the top of the hill, you have a certain amount of gravitational potential energy, or gravitational potential. And at the bottom of the hill, you have a difference, right? And that's the whole fun of a roller coaster, is the fact that you go from places where you have a lot of potential to areas that you have less potential. Same thing goes on with electricity. You have, in parts of a circuit, places where you have a great amount of potential to places that you don't have much potential. And you can measure the difference between those in what's called potential difference, sometimes also called voltage. The units for electric potential or voltage is a volt, and is defined as 1 joule. Remember, joule is a unit of energy. And remember, a coulomb is a unit of charge. So it's the amount of energy per charge. And as I'm going to talk about when I discuss circuits here in a few slides, I like to envision in a circuit charges being like little army guys that are marching through the circuit. And of course, army guys have little backpacks. And so I like to envision voltage as being the amount of energy that has been given to each army guy. So if you've got a 6-volt battery, the 6-volt battery is giving 6 joules of energy to each Coulomb, or each charge. Each army guy has 6 volts of energy, or 6 joules of energy placed in his little backpack, which then he can carry around through the circuit to deliver it to somewhere that needs energy, such as a light bulb, a motor, a fan, etc., etc. So what do you think of when you hear the term current? For many people, you maybe think of a river or a stream, right? What what does current mean in a river or stream? Essentially it means flow. You could put a little, you'd put a marker across the stream or some measuring device, and then measure how many gallons of water pass by that checkpoint every second. Well, same thing with electricity, but in electricity, instead of measuring gallons, you're measuring the amount of charge that passes by a checkpoint in your circuit every second. So current is a measure of the flow of charge, and the unit is an ampere, and an ampere is 1 Coulomb of charge per second. One ampere is 1 Coulomb of charge per second. And it turns out, since each electron has a tiny little charge, that would mean a huge amount of electrons passing by a checkpoint every second in order to have 1 amp of current. One thing you'll also come to discover is that if you're imagining the army guys as being your charges, your electrons, they really don't move through a circuit very, very quickly. The individual electrons don't, because they're constantly bumping into stuff. But one thing that is important for you to understand is that even though the individual electron does not move very quickly through the circuit, the electrons can pass the energy off, the energy they're carrying can be passed off from one to the next. So the energy that flows through a circuit moves essentially at the speed of light. And that's why when you flip on a light switch, even though the charges that make up, that are in those wires, that's in the switch, that's in the light bulb, even though those individual charges move relatively slowly, they can still pass the energy essentially at the speed of light, which means there's no time delay between flipping on a light switch and the light bulb actually turning on. Okay, so 3 main concepts that you have to understand in order to deal with electrical circuits. One being voltage, which we've already talked about. Voltage, I think about sometimes as being the amount of energy that each charge has. Another way of thinking about it is essentially the amount of push, the amount of electrical pressure. Just like in a fluid, if you have a hose, you get more flow if you turn the faucet up, right? You get more water flowing through the hose if you turn the faucet up. If you increase the pressure, you're going to get more flow. That's another way of thinking about voltage. It's essentially the amount of push, the amount of electrical pressure given to the circuit, usually by a voltage source, a battery, power, some sort of a power supply. We've already talked about current, the amount of flow that you get through a circuit, the amount of charges that pass every second past a checkpoint. The last thing, the third term, is resistance. Resistance is very much like it sounds. It's a opposition to the flow of charges through a circuit. Different materials have a different amount of resistance. As we've already talked about, things like insulators, like wood or certain plastics, typically do not have that many free electrons in them. And of course, it's the free electrons that are those are the charges that move through a circuit. So obviously, a wood, any kind of insulator, rubber, another good example, those are all materials that have a huge resistance. They don't allow charges, they don't allow current to flow through them very easily. Whereas metals are good conductors. They have very low resistances. In fact, for the metals that make up most of our connecting wires on our circuits, we're going to essentially assume that the resistance of those conductors is 0. Makes it a little bit easier for doing calculations. Essentially, resistance describes how well something allows charges to flow through it. Okay, so one thing you're going to be dealing with in the lab activities is you're going to have to use two different types of meters, an ammeter and a voltmeter. And they do different things and they are wired differently in the circuits. An ammeter measures current. It measures flow. It measures how many charges are moving through the circuit at any particular, per second at any particular time. And the important thing with ammeters, and I'm going to actually label which one's the ammeter. The ammeter over here, we've got actually two depictions. We got the more real-world depiction over on the left. We have what's called a schematic diagram on the right, which I can't draw batteries and real meters very prettily, so I'd much prefer drawing electrical circuits using schematics. But anyway, an ammeter is wired in what's called series or in line with your circuit, because remember what the ammeter's job is. An ammeter is going to essentially count the number of army guys or the number of charges. Remember we talked about, there's the circuit is full of army guys. I'm going to put little dots here. It's full of charges, right? The charges are in the wires, the charges are in the filament of the battery, the charges are in the ammeter itself. There's charges everywhere in the circuit. Blah, 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 blah. And those are all my little green dots there. Okay, so the circuit is full of charges. And what our ammeter wants to do is it wants to count the number of charges that are moving through it every second. And so it's got to be part of the circuit. It's got to be able to count all the charges moving through the circuit, the rate at which the charges are moving. And so essentially you can set up a checkpoint in the ammeter, and it's going to count the number of charges. And it turns out in a circuit like this, the number of charges that are moving through the ammeter is the same. You couldn't have more charges moving through the ammeter than you could over here or over here. The flow, or through the battery for that matter, the flow must be the same everywhere, because if it were different, if I had more flow, let's say at this spot that I'm labeling it as X, if I had more flow there and less flow at my ammeter, I'd wind up having a buildup somewhere in between, because I'd have more charges flowing through my X point than I would through my ammeter, and eventually charges would start building up, and that just does not happen. You don't have, just like water doesn't, or if you have water building up in a pipe, it's going to expand and burst, right? So the flow has got to be the same everywhere. So if I measure my current at the ammeter, I'm pretty confident that the flow there is going to be representative of the flow everywhere else in my circuit. But that's the way an ammeter is wired up. It's wired up in series or in line with your circuit. The voltmeter is the other meter you'll be using in a couple of the lab activities. The voltmeter has a different job. Instead of counting the number of army guys that are moving past it, right? I already labeled army guys as being these little charges, these little green dots in my circuit. Notice that the voltmeter is wired up differently. It's not part of the main circuit, right? Notice that it's not part of the. I'm outlining the main loop here with my green dots, and notice that my green dots do not go through my voltmeter. What my voltmeter does, it doesn't count army guys. What it does is it conducts a little interview. It stops a charge over here on one side of the light bulb, stops a charge there and says, hey, how much energy do you have? Because remember what voltage is. It's the amount of energy per charge. So it does a little interview. It says, hey, charge, how much energy do you have? And that charge is going to give it an answer. It's going to say, well, I just came from the battery. I've got a full backpack full of energy. And then he's going to tell, once he's conducted the interview, the voltmeter says, okay, charge, go on your way. And he's going to grab another charge over here on this side of the light bulb. He's going to say, at the same time, he's going to say, hey, how much energy do you have? And that charge is going to say, well, gosh, I just helped to light up this light bulb. I just gave my energy to that light bulb. In fact, I've got no energy because, in fact, I'm connected to, notice where this charge is going. He's going to the negative side of the battery. The negative side of the battery, those are all charges that have no energy. And so this guy also has no energy. And so the voltmeter is going to be conducting this simultaneous interview with one charge over here, full of energy, another charge over here who has no energy in his backpack, and the voltmeter takes the difference between those two answers and reports that as the voltage, or the voltage drop across the light bulb here. Another way of saying that is the potential difference between this spot to the left of the light bulb and this spot to the right of the light bulb. That's what a voltmeter does. So notice that instead of being wired in series, it is actually wired in what's called parallel to the circuit. It's wired across the light bulb. Okay, so in order to understand why you can get shocked by stuff, let's think back to the comparison between gravitational potential and electric potential we talked about. You know, imagine you're standing on the top of a tall roller coaster hill, or even the top of a tall skyscraper. When you're standing up there, you've got a large amount of gravitational potential, right? But notice that your entire body is at the same potential, right? You're at the same height, and therefore you're not hurt. There's no danger there. But what if you then change your gravitational potential really quickly, going from the top of the building to the bottom of the building, like falling? You change your potential, and that would be kind of bad, right? Well, same thing happens with electricity. In this case, we have this bird. This bird is shown, he's got both feet on this wire, and the wire might have 50,000 volts, right? He's got a huge amount of electric potential, but notice that his entire body is at the same potential. It's like he's at the top of a building, right? Same analogy. It's only when you create a difference across your body that you get into trouble. So if he somehow grounds himself, grounding is another way of saying that you've got an electrical potential of 0. And so if all of a sudden he has a right foot that is at 50,000 volts of potential, and then a left foot that's at 0 volts, now he's got a potential difference. And anytime you have a potential difference, that's going to create a flow of charge through the critter, in this case the bird. And that's usually what kills you, is the current. When you have too much current flowing through your body, that's when you start having problems with your heart. Usually you go into cardiac arrest and potentially die.
Okay, so I'm going to demonstrate a very basic, it's called a simple circuit. The reason why it's called a simple circuit is we only have one source of energy. In this case, it's a battery. It's a D-cell battery. I only have one user of energy, or a load. In this case, it's going to be the light bulb. And then I've got a few connecting devices, wires, that will take the energy from the battery and take it to the load. But notice right now nothing is happening. And that's because I don't have a complete circuit. Notice that my positive end of the battery and the negative end of the battery, there's nothing attached to them. Of course, I do have these wires here, and I have the other ends of these wires. So I'll take my black wire, and notice I can connect it to the negative side of the battery. But notice that doesn't do me any good. There's nothing happening yet because I don't have a complete circuit. It's only when I connect my red wire to the positive side of the battery that all of a sudden my light bulb lights up. I have a simple circuit. Energy is able to go from the battery through my conducting wire, doesn't really matter which one you want to envision, to the light bulb holder, and from the light bulb holder through the filament of the light bulb. And that light bulb filament is actually a resistor. And as those electrons try to work their way through that light bulb filament, they give up energy. They give up electrical energy, and it turns into heat energy. It lights up the light bulb. Okay, so here's another depiction of the simple circuit. Again, notice I've got a power supply. In this case, it's 2 batteries, but we just use 1 battery. And I've got a light bulb, and then I've got some connecting wires. So on the left, you actually see a pictorial diagram. And on the right side, you see more of what's called a schematic diagram. Notice I've got a long line and a shorter line. That's indicative of a battery. And this is considered to be a bulb here. And then, of course, this is all connecting wire. So one thing that's very important for you to understand is you should see these little shaking dots. Those shaking dots are my charges. Those are my electrons. And hopefully you realize that in a complete circuit, everything is made of metal. The connecting wires are made of metal. The light bulb, the little prongs that are in the light bulb, the filament itself is made of metal. The battery is made of metals. And so everything is full of metals, which means everything is full of free electrons. And that's what we're seeing here. We're seeing all those little shaking dots. Those are free electrons. But notice that those electrons really aren't moving at all because we don't have a complete circuit. So they're just kind of moving around randomly. And notice that some of them have red around them. Those are electrons that have energy. They're on the positive side of the battery. They have energy. And I think I may have explained about my vision of the Army guys. Well, those are Army guys who have full backpacks. The problem is they don't have any marching orders. They don't know where to go. So they're just kind of standing there with full backpacks, full of energy, but nowhere to go. Now notice what happens when I start to make some connections. I'll connect the red wire first to the battery. Now all of a sudden, not only do the guys on the positive side of the battery have energy, backpacks full of energy, but all the charges that are in this wire, they're all connected to the positive side of the battery, and therefore they're all energized. They all have backpacks full of energy. But notice that I don't have a complete circuit. Now what happens when I connect the wire to one side of the bulb? Now all of a sudden I have more electrons that have energy, but yet we are not producing light yet because I don't have a current. I don't have any flow of electrons. And why don't I have flow? Because there's nowhere for these electrons to go. I've got open breaks in my circuit. I have an open circuit right now. I continue to make connections. Notice that now I've got a lot of energized electrons, but still nobody moving, and therefore no current, and therefore no glow. Here's my last connection I'm going to make, and all of a sudden once I make that connection, notice that now my charges are moving, and once they're able to move, they're able to carry energy from the battery to the light bulb. At the light bulb, that energy is used up and turned into light and heat energy. And notice the electrons, after they get through the bulb, they continue to move. But they have no energy. They've got to go back to the battery in order to get restocked, to get their backpacks filled up again. This is a simple circuit. Okay, so far we've created a simple circuit involving just one bulb and one battery and the connecting wires. What we're going to do now is we're going to actually increase the level of complexity. We're going to create what's called a series circuit. A series circuit is when you have more than one load. In this case, I'm going to have this bulb and this bulb. The important thing with a series circuit is that you only have one path for the charges to move. And so I need to actually, one thing that you'll notice is, look at these little silver plates. These are all conducting materials. These are all aluminum. So what I need to do is, in order to create one single path, I have to arrange these so that I wind up with one big old loop. And so let's see, what can I do here? That one. There we go. Okay, so what you're going to see is that I'm going to now create a path so that, put my other wire up here, so that energy will come out of my battery, and it really doesn't matter which side we connect to, but it's going to come out of the battery, come through this black wire to this metal plate. Of course, this goes on. This is not connected to anything. So the charges have no choice. They must go this way. The energy must go this way through the first bulb, along this conducting path, through this bulb, and then through this wire, because this one again is going to wind up going off into space. There's no real path there, and so I'm going to force the charges now and the energy to go through the red wire and back to the battery, and we'll see what happens. So I'm going to connect the battery, try to connect the battery. And what you should notice is that those lights are just barely glowing. See just a little glow to them. It's very, very dim. That's one property of a series circuit. Notice if I move my wire over here, much brighter, right? Well, why is that? Because my energy is coming into this wire through the bulb, but then going right back to the battery. Those charges go right back to the battery. They only have to lose their backpacks full of energy at one spot, just through this bulb. Because notice they don't even have to go through this bulb in order to get back to the battery. That's a simple circuit, but if I, again, force those charges to go through both my bulbs in order to return to the battery, now they have to kind of divide the energy. The energy that's in their backpack, they can't just dump it all across this one bulb. They must share it between these two bulbs. And so therefore, they only have so much energy in the backpack. And so when they share it across both bulbs, they just barely light up. That's a series circuit. Now I could actually add a third bulb in here if I wanted to. Because notice I created a big old S path. So I could actually connect my wire across that third. So now notice I'd have energy and charges moving through this first bulb, going through the second bulb, going through the third bulb, then back to the battery. But notice that I'm dividing my energy by so much. I'm dividing it 3 ways that even though those bulbs are indeed consuming energy right now, it's not enough energy to make them glowing enough that we can see them. So therefore, that's a series circuit that has, as you're going to find out, a very low current. It turns out as you add more and more bulbs in series, you actually increase the overall resistance of the circuit and therefore decrease the flow. I like to give the army guy analogy, where one single bulb is not too much resistance, and therefore you're going to have a lot of charges flowing and giving it energy. Each one has the same amount of energy in his backpack, but there's a lot of them flowing through that filament at any 1 second, and therefore a lot of energy being delivered to that light bulb, and therefore it glows. But as I add more resistance, I'm forcing now those same charges to now go through 2 bulbs, and by increasing the amount of resistance, I lower the flow. And so even though each guy, first of all, now the guys are dividing their backpacks among 2 bulbs, so they're not giving their entire backpack to each bulb, and there's fewer army guys marching through the circuit because there's more resistance here. And therefore, less energy per guy and fewer guys marching through results in dimmer bulbs. Those are the characteristics of a series circuit. Okay, so I'm going to start this this video is going to be about parallel circuits, but I want to start you off with a series configuration. So let's imagine that I hook up a battery and I'm going to hook it up to these 3 bulbs in series. Notice that, again, I have one big old path. I would force the charges, they would have to move through this conductor, through this bulb, through these conductors, through this bulb, through these conductors, through this bulb, in order to get back to this wire, taking me back to the battery, to get reloaded with energy. It's one big old path, and the charges have no choice. They must go through all 3 bulbs. Now, that's a series setup. Let me go ahead and swing these connectors back around to show you what a parallel setup looks like. And notice, essentially it looks like, instead of an S here, it looks like an 8, right? Figure 8. So now, I could hook up, let's say, put my wires there. So imagine what's going to happen. A charge with energy is moving through here. He moves through this first bulb, lights it up, of course, and then what are his options? well, I guess he could go through this bulb, but he does not have to. And electrons are lazy. They always take the path of least resistance. So rather than going through this other resistor, why not move through these conducting wires, which essentially have no resistance, and get to this other wire, which takes him back to the battery. Notice that he only has to go through this bulb. Or maybe not this bulb. What if he, instead of going through this bulb, what if he went this way? Notice these are conductors too. Couldn't he go through this bulb instead in order to get over to this red wire and back to the battery? Or couldn't he just go through this bulb and back to the battery? Notice that I'm giving my electrons choices. They don't have to go through all three bulbs this time. They can go through just one. They must go through one, but that's all they have to go through. So notice what happens when I now attach my battery. Hook up the other sides of my wires, and notice what happens. All three bulbs light up. I know the one is kind of out of frame there, but you can see it's glowing. They're all lit up. In fact, notice how very brightly they're glowing. Aren't they glowing just as bright as when I just had one single bulb in a simple circuit? Isn't that interesting? Why is that? Because notice that, in fact, I'm going to go ahead and disconnect these other two bulbs just for you to see that even with those two bulbs disconnected, notice my one bulb lights up bright. Add a second bulb in here. Now both bulbs glow just as bright. Add a third bulb in here. All three bulbs glow just as bright. Okay, so I wanted to give you a little demonstration of a parallel circuit. Well, actually, this is not even a parallel circuit at this point. Notice what we have here. We've got a battery pack, we've got a bulb, and we've got a second bulb, but one thing we need to notice right off the top is that the second bulb is not attached right now. There's an opening in the circuit. So therefore, we really only have a simple circuit. We have a battery pack that's attached to a bulb and then back to the battery pack. So we have this inner loop, and notice that we do have charges moving through that inner loop. And because of that, our light bulb is lit up. Right? So these charges they're given energy at the battery. That's why we have these little pink circles around them. And then that energy is given up when they given up to the light bulb as they move through the filament. And so the charges over here have no energy, and they get restocked. So again, this is the little army guy analogy. Works for some people, doesn't work for other people. But our army guys are moving through this inner loop. Notice that nobody's moving in this outer loop. Why not? It's an open circuit. I have this opening. What happens if I do attach this? Now all of a sudden, both bulbs light up. I have charges moving through both loops. Let me detach it, reattach it. And you should notice a couple of different things. First of all, I do have charges moving through this second loop now. Notice how the flow through my battery has changed when I am connected versus not connected. Notice that I've got a difference. They're flowing slower right now than when they're connected. Now I've got more flow going through the battery, right? Well, why is that? It's because now both of my branches are demanding current. It's like opening up a second shopping line at a grocery store. When everybody's backed up, how do you get more flow? How do you get more people through the store? Well, you open up two shopping lines. That way they can be processed more quickly. You know, the flow through each of the shopping lines is the same, but notice that I can get more people out the door now, right? So that's one way of looking at a parallel circuit. And notice that we see that on our ammeters. When I only have this simple circuit, I have 6 volts of push. My batteries are providing 6 volts of push, and I wind up with 1 amp of flow. Notice I have an amp out of the battery, and then through this branch. If I had a little ammeter right there, I'd have 6 amps of flow. I'm sorry, 1 amp of flow through that inner loop. Now notice what happens. So I've got 3 ammeters. This ammeter is measuring essentially the amount of current here out of the battery. This ammeter is measuring how much current through just this branch. This ammeter is measuring how much flow through this branch. Notice there's no current right now. Watch what happens when I attach. Now all of a sudden, this branch is demanding 1 amp of flow. This branch is demanding 1 amp of flow. And therefore, how much has to be coming out of the battery? 2 amps of flow to meet the needs of both those branches. It turns out that unlike a series circuit, where as I add more and more resistors, my flow decreases, in the case of a parallel circuit, as I add more and more resistors in parallel, I actually increase the flow coming out of the battery.
Up till now, we've been treating connecting wires as being perfect conductors, having no resistance. But in reality, a copper wire does have resistance. And of course, its resistance depends upon its length and its diameter and all that kind of stuff. But it does have a non-zero resistance, which means that it does, when you run electricity through it, as you're running electrical energy through a conducting wire, it will start to turn electrical energy into heat energy. It'll start to heat up over time. The more current you run through it, the hotter it's going to get. And it turns out that if, especially as you see with parallel circuits, when you start to put a lot of loads on a particular circuit, the circuit that's going into your kitchen, when you plug in the blender and the toaster and run the microwave, and you do all this stuff at the same time, it starts to demand a lot of current. And all those individual demands add up to being a large amount of current for the circuit. And if you demand too much current, you could potentially heat up those wires, melt the insulation, and then you've got bare wires, hot wires inside your walls, which could start a house fire. So there are safety devices that have been developed over the years to prevent this. The first safety devices that were developed to prevent house fires were safety fuses, and what was called the old fuse box. Not many people have fuse boxes anymore, and there's a couple of reasons why people don't have fuse boxes anymore. First of all, fuses are kind of like incandescent light bulb filaments in the sense that they're made out of metal. And in fact, we've got a little band inside the fuse, and this is all made out of metal, and so it's going to conduct electricity. A current's going to be able to flow through that fuse. But very much like a filament, this band inside the fuse can eventually, if you run too much current through it, it's going to get hot and it's going to melt. And when it melts, of course, you're going to have a break in the circuit. When this thing melts, boom. Now you've got a break, you've got an open circuit, current is no longer going to flow. So it's going to serve its purpose. It's going to shut down the current in the circuit and hopefully keep your wires from melting and starting a fire. The problem is now you've got a fuse that has a broken ribbon in it, and therefore you need to replace it. And that's where the problem came in, is that quite often people did not have a huge supply of fuses on hand. So when they would run too much current in the kitchen and they'd blow the fuse, they'd have to replace that fuse. Well, what happens when you run out of fuses? Well, either you have to go all the way to the store or you'd look for a workaround. And all too often people would put pennies in their fuse boxes where the fuses were supposed to have gone, because essentially the penny would make the connection. You know, there's the connection here and a connection here, and they would put a penny right in between there. Let me do it in, I don't know, orange. They put a penny right in here. Of course, pennies are made of copper, at least at the time they were made of copper. Now they're made out of zinc, but they would still conduct electricity. And so now you've got a penny that's going to make the connection for you, but unlike a little fuse ribbon, which will heat up and melt when you run too much current through it, a penny, you can run a lot of current through it. And so therefore that essentially gets rid of the entire point of having a safety device, that you might as well just have a plain old wire running through there. So fuses were unreliable because people didn't keep a good stock of fuses on hand, and they would start putting pennies in and you would get house fires. So therefore circuit breakers were invented. And the nice part about a circuit breaker is that it is reusable. What happens when you run too much current through your circuit, it's going to flip the switch. That switch can be reset. Of course, if you continue to make the same demands of the circuit, it's going to flip over and over and over again. So hopefully you make corrections for whatever the problem is. If you're drawing too much current, if you're trying to run too many things at the same time, you just don't do that, and you won't have the circuit tripping all the time.
Okay, so I hope you tried to light the light bulb yourself before you came to look at this video, but hopefully you saw, and I'm going to try to give you a nice close-up view of the light bulb. Inside that light bulb there is a filament that we're hoping to get to glow. You'll also notice there are two posts, and those two posts are very important because the one post is connected to the bottom of the light bulb, that little nub there, whereas the other post is connected to what I call the housing, this casing that has the screw part. Don't notice that the housing is made of metal, the nub is made of metal, but in between there's an insulating material. It's a type of glass in between the two so that they are not connected electrically. That's very important because turns out that even though we're used to seeing a light bulb screwed into a socket where it looks like there's only one connection, by screwing it into a socket you're actually making two connections. You're connecting to the nub and you're connecting to the housing. And that's what we want to do in order to light our light bulb. So the first thing we need to do is to take our wire, and I'm going to attach the one end of the wire to the housing, the screw-in part. Then I'm going to put the nub part on one side of my battery. It doesn't matter which side, positive, negative, doesn't matter. Then the important thing is that I'm going to attach the other end of my wire to the bottom. And notice, when I do that, I have completed the circuit. Current is able to flow through the filament of my light bulb. It heats up that filament to the point where it is glowing. It's producing visible light. Now, a light bulb appears to have only one connection, but what if we chopped it in half? What you would see when we chop it in half is that the outer casing, the thread part, acts as one connection. The nub at the bottom acts as the other connection. And the brown stuff in between is essentially glass. It's an insulating material that keeps those two conducting paths separate. So when electrical energy carried by electrons moves through the one wire and through the filament and down through the other post and out the nub and into the other part of your light bulb holder, you have a complete circuit. Notice there's one full complete path for the electrical energy to travel. Without that full path, we would not have a circuit and the bulb wouldn't light. And there we have it. When I remove, I break the circuit anywhere and I'm not going to have a glow. Notice if there's really no other way for me to attach this properly in order to make the complete circuit that creates the current, which then produces the light in my bulb.